Hi, everyone. Welcome back to MATA02, the magic of numbers. So we only have 2 more weeks of lecture left. So there's this Monday, Wednesday, and the next Monday and next Wednesday. And we only have 2 more topics really in this class. One of them will be today, where we're going to be talking about primality tests. And the next will be starting on Wednesday and through like next Monday and Wednesday, we'll be talking a little bit about applying all of this number theory that we've been learning to cryptography, so internet security. So I should mention that on this coming Wednesday, so 2 days from now, that will be one of the more interactive lectures. So I know a lot of you all have been coming online instead of in person. I'm just going to warn you that on Wednesday, you will not get the full experience online because I will be having you guys break up into groups and like sending messages to each other and trying to break each other's cryptography. So just a forewarning, please show up on Wednesday. Otherwise, I mean, you can look at the notes, but they won't be the full experience. Okay, so Fermat Primality tests. What's a prime number? We've covered this a bunch of times at this point, but a prime number is any number, any natural number greater than 1 that is divisible by only 1 and itself. So for example, 7 is prime because it is divisible by only, oh, sorry, it's not divisible by 2, 3, 4, 5, or 6. Okay? And of course, prime factors form the multiplicative building blocks of the natural numbers. So 24, if you break this up, that's 4 times 6, 2 times 2, 2 times 3 is equal to 2 cubed times 3. So prime numbers are super useful. And of course, because of the sort of properties of prime numbers as building blocks, you only need to check 2, 3, and 5 to determine if 7 is prime. Okay, but now let's suppose I want, so let's try for finding prime numbers. Suppose I want to find a pretty big prime number. How can I do that? Which of these algorithms have we learned would allow us to find a prime number? So these are all things that we've learned in this class. Which of these is the correct way of finding prime numbers? Is it the Euclidean algorithm? Is it the sieve of Eratosthenes? Is it the Pythagorean theorem? Or their SPI function? Or none of the above? Okay, so it looks like some people are starting to guess that it's B. Well, let's just go through what each of these different things do. Just as a reminder, since we have learned most of these things in this class. So one is the Euclidean algorithm is, of course, for finding greatest common divisors. So we've done that over and over and over again, and you will continue to do it over and over again on the final. The Pythagorean theorem, hopefully you all know, this is about sides of a right triangle, which we didn't really cover so much in this class, but should be very familiar to everyone. And the Euler's phi function, which is finding numbers of relative primes. Whereas this here is actually finding primes. Okay, and let's review this a little bit, because this is the only tool we've learned so far for actually finding prime numbers. So this is, of course, this is a slide from one of our previous lectures. This is, of course, a method for computing the list of primes by filtering out all multiples of a number. You repeatedly filter out all multiples of the smallest remaining number in the list. So you might start out with multiples of 2, then multiples of 3, multiples of 5, because 4 is already filtered. And so basically each step you're filtering out all the multiples, and then you're left with just the remaining primes. And this is often credited to Eratosthenes of Cyrene from around 200 BCE. And well, we saw this in action, but let's remind ourselves of how it goes. So if you have all these numbers from 1 to 100, you might start by starting from 2, and then of course, so 1 is special, so we're going to ignore 1. Start from 2, and we're going to remove all the multiples of 2. And so those are all gone. And then, of course, we are left with 3, and then we want to remove all the multiples of 3. So, well, 3, you might remove 6, 9, 12, 15, 18, and so on. So let me just cross all the multiples of 3 out. I'm going to cross it out this way so it's a little bit faster for me to see the pattern this way. Well, these are all the multiples of 3, of course. And 60, 69, and 90. And then, of course, we have 5, and we want to cross out all the multiples of 5. So luckily, that's pretty easy. Let's just these 2 columns. And you notice, of course, that as we're crossing them out, we've already crossed out most of the multiples because they're also multiples of some other prime number. And once we come on. Sorry for those. There. Okay, great. Sorry, technical difficulties. But yeah, so but then when we get to 7, well, let's see. We've already crossed out most things. So let me do a different color. 7, we crossed out 14, 21, 28, 35, 42. The first number that we successfully crossed out from 7 is this 49 here. And then let's see, where is 63? Oh wait, I skipped one, didn't I? 56, 63, 70, 77. So we successfully crossed that one out. 84, 91, successfully crossed that one out. 98. So you notice that as we go on, we're crossing out fewer and fewer numbers. And of course, once you get to 11, then you're not actually crossing out anything interesting because all those numbers are already crossed out from 1 to 100. And of course, this goes back to the question we talked about how quickly do we get all the primes between 1 and 100? And the answer is pretty quickly because you only need to cross out numbers that are, well, the multiples of prime numbers smaller than 10. And this is one of the results that we gave earlier. And let's actually prove it. So if n is not prime, then it must be divisible by a prime p that's less than or equal to the square root of it. So if you're talking about a number like 100, you only need to go up to prime smaller than 10. And the reason for this is pretty straightforward. So now that we know about proofs, we can just write out a direct proof. So let p be the smallest prime that divides n. Divides n. Okay. Well, then we know let n is equal to p times k, where k is greater than or equal to p, right? Because p is the smallest prime, and so when you break it up, well, clearly k has to be greater than or equal to p. Well, then we just plug that in. So we know let n is equal to p times k, which is greater than or equal to p squared. Because, of course, if you substitute it in k for p, or sorry, p for k, it's going to be something that's smaller. Which, of course, implies that n is greater than or equal to p squared, which implies that p is less than or equal to the square root of n. And the punchline to that, which we already covered before in this class back in lecture like 4 or something, is that to find out if a number n is prime, you only have to run the sieve up to a prime p less than or equal to the square root of n. So as an example, if we're asking, is 97 prime? Well, you just need to check. You need to check 2, 3, 5, and 7. So, well, 97 divided by 2 is 48, remainder 1. 97 divided by 3 is 32, remainder 1. 97 divided by 5 is 19, remainder 2. And 97 divided by 7 is 13, remainder 6. So the answer is yes. Which you could also see from the previous slide where we actually ran it for all numbers. But if you're just checking if a particular number is prime, you only need to check all these small primes, right? Okay, so let's all review so far. So let me ask you another question. Is the following number prime? So this is a number, right? And it's not even that big. I can write it all out in one line on the PowerPoint slide. Is this number prime? And how would you try to figure that out? Any thoughts? So just so that you don't have to count them one by one, if we call this number x, this is 42 digits long. So x is around 10 to the 42, so it's bigger than that. Okay, so it does end in a 7. People think that this number is not prime. How would you know that this number is not prime? Your only thought is that this number stresses you out. Well, it is a really big number. And to be honest, when I wrote this number down, I wasn't sure if it was prime or not. I just randomly typed in numbers on my keyboard until I got a number that was 42 digits long. And yes, these are pretty big numbers, but it turns out that when you're working with, you have to square root it. Yeah, so now you're getting to the sort of ideas that we're talking about in the sieve. But like when I was writing this number out, it was because I wanted a relatively big number, because these are the sorts of numbers that your computer works with when it's dealing with cryptography. It turns out that numbers this big also stress computers out. And that's what's really cool about them, is numbers this big, figuring out if these kinds of numbers are prime is something that stresses computers out. And because computers aren't good at doing this kind of thing, that's what makes cryptography possible. Because it turns out that with cryptography, what you want is you want some hard problem. And turns out there are a lot of hard problems in math. And don't worry, we'll be covering this more on Wednesday and next Monday about why using hard problems is super helpful for cryptography. But for now, let's just try to figure out how long this would take to determine if it's prime using the sieve of Eratosthenes, if it takes, say, 1 second to remove the multiples of each prime. So I'm going to ask you to choose the best approximation. And yes, a hint is that something about the square root does make sense. Like that was a good thought, whoever it was who had that idea. So how long does it take? If you had a computer that would take a look to see if it's divisible by 2, and then remove all multiples of 2, and then remove all multiples of 3, and then all of 5, and all of 7, and so on. Would it be pretty quick? Would it take like 21 seconds or 42 seconds? Or would it take a long time? Would it take 30 trillion years? Or would it take even longer? Would it take, how much is 10 to the 34? Quintillion is 5, quintillion, sextillion, septillion, octillion, decillion, indecillion, something like 3,000 indecillion. I forget my Greek prefixes, but okay, so people seem to think that this would be pretty quick if it takes 1 second to remove each multiple of each prime. That is not actually the case. So what do we need to check? We need to check up to the square root of n, right? How big is the square root of n? Well, of x. X is around 10 to the 42. So the square root of x is approximately, so I'm the square root of 10 to the 42, which is approximately 10 to the 21. So it would actually, if it takes 1 second to remove the multiples of each prime, and if it takes 1 second to check if it's divisible by each number, let's say, then it would take actually around 30 trillion years. Because of course we need to check all primes up to 10 to the 21. So you need to first figure out what all the primes are from 1 to 10 to the 21. And then you need to check if this particular number is divisible by each of them. So somehow we've been dealing with all these things in class, and we've been like, oh, well, yeah, well, you can sort of brute force it with a calculator because we've been dealing with small numbers. But once your numbers get a little bit bigger, and this number isn't that big, it's big enough that it's small enough you can write it down easily, all of a sudden, it's going to take you 30 trillion years if you take only 1 second per divisor to figure out if this is prime. And I don't know about you, but I would rather not wait around for 30 trillion years. Now, of course, you might have a faster computer. So maybe your computer can do 1,000 each second. And if you can do that, then it'll only take you 30 billion years, which is slightly better. Or maybe 1 trillion a second. And then it'll only take you 30 years, which, I mean, is within our lifetimes, but still not exactly what we want to do. So now the question becomes, there are a couple of questions. One is, can you figure out if this number is prime? And two, if you just want to find a large prime number, like how do you find a large prime number? So sometimes there are uses that you'd use for a prime number, because prime numbers have all sorts of special properties, and so you just need to find one. You don't need to check if a particular number is prime. You need to figure out if you can find a prime number. Any questions about all that? Okay. So, well, luckily, we have a lot of theorems surrounding it, and there are other methods that you can theoretically use to check if something's prime. Oh, so how did we determine that that was prime? Oh, for the record, this number is not prime. But I will show you, but the point of today's lecture is we can show you that there are ways of proving that the number is prime or not prime that don't involve checking everything. Of course, if this number ended in a 2, it would be pretty easy to show it's not prime, right? Because then you know it's divisible by 2. And so this isn't, won't necessarily take 30 trillion years. Maybe this number is divisible by a small number, in which case you would check it pretty early on. But if it is prime, then checking it would take a really long time because you need to check all the divisors and stuff. You know that it's not divisible by any of them. Now, don't worry, we'll come back to this number. But first, let's remind ourselves of the prime number theorem, which I covered in class one day, some number of weeks ago. So this was proven in 1895, 1896. And it's basically there are approximately n divided by the natural log of n prime numbers between 2 and n. So what does that mean? So that means that between 2 and 10 to the 21, there are approximately 10 to the 21 divided by a natural log of 10 to the 21, which is approximately 2 times 10 to the 19 primes. Okay, because most numbers aren't prime, but when you have 10 to the 21 different possible numbers, it turns out that still a very large fraction are prime. You still have 2 times 10 to the 19 primes, which is, quintillion, sextillion, which is like 20 sextillion primes. So on the previous slide, we can check fewer numbers since we only check primes, but that's still 2 times 10 to the 19 primes to check. Primes to check. So at 1 a second, 1 per second, still 6 times 10 to the 11 years. So 600 billion years. And at 1 billion a second, that's still 6 times 10 squared years, which of course is equal to 600 years, or 6 centuries. And that is just way too long to wait. So these are problems that, the point I'm just trying to make is that this kind of problem, asking is a number prime, is hard even for computers. Because even though computers are really, really fast, and you can do lots of operations over and over again, actually running this algorithm is going to take you way too long to actually succeed. Okay, so this is not so great, right? Because we talked about how the primes are so much the building block of mathematics and number theory. And they have all sorts of useful properties, from being building blocks in multiplication to having special properties when you're in modular arithmetic, right? So we've talked about so much how when you're in a prime modulus, all sorts of nice things happen. But what do you do if you can't figure out if numbers are prime? Well, one thing you could do is maybe you can just guess that it's prime. So you don't know that it's prime, but what if we just said that it's prime? What's the chance that we're right? So I wrote down this number, and I'm just going to say, okay, well, I claim that it's prime, and because it's really hard to prove that it's prime or not, it's really hard for you to disprove it. What's the chance that I'm right? So here, I recall that the prime number theorem says that approximately n over log n numbers are prime from 1 to n. So if I guess one big number, what's the chance that I guess a prime number? So I'll have you all try to figure that out. You may need to use a calculator, but what's the chance that this big number is prime? Just from knowing the prime number theorem about how often numbers are prime. And as a reminder, this is about, you can say this is about 10 to the 42. So some people are guessing that the chance is actually really, really small. So if you're guessing D, oh, that's the natural log of n. So you should have a button on your calculator that says like ln. That's the natural log. But so if you're guessing that it's a 1 in 10 to the 21 chance, you're basically saying that there's almost 0 chance that it's prime. But remember, the whole point is the prime number theorem says that there are a lot of prime numbers. There are n divided by log n primes between 1 and n. Okay, it seems a lot of people have guessed that the chances are actually super duper low. And let me just say that if I gave you a random number between 1 and 10 and asked you, is this number prime, what would the chances of that be? Yeah, so you have 2, 3, 5, and 7. So the chances would be 4 and 10 if I gave you a number between 1 and 10. Now, suppose I gave you a number between 1 and 100. What would the chance be? So obviously, you'd have to look at a list of all the prime numbers between 1 and 100, but the chances aren't that low. I think there's something like 20 or something. I don't actually know how many there are. But now, from 1 to 10 to the 42, it turns out that there are actually a lot of prime numbers. And so your chances aren't so bad because n is approximately, let's say, 1.2839 times 10 to the 42. So natural log of n is about 97. So this means that there's about a 1 over 97 chance of it being prime. So basically, on average, about 1% of numbers between 1 and 10 to the 42 are prime. And so if I pick this big number, I can still say that there's about a 1% chance that it's prime, which isn't so great, right? But it's not terrible, because that means that if I pick, say, 100 random numbers between 1 and 10 to the 42, chances are that one of them is prime. So if I just need to find a prime number, and let's say you're taking a test, and the test is, give a prime number, you're allowed 100 guesses. Well, chances are that you would succeed in getting a prime number by just picking 100 random numbers. Does that make sense? I think this is a little bit confusing of a concept, so please ask me if you're having trouble with this or you need me to explain it slightly differently. So again, the basic idea is that prime numbers are rare, but they're not that rare. And so there are a lot of prime numbers. And in fact, so if we go back to, let me see, where's that slide? If I go back to the slide here, you notice that there are actually a lot of prime numbers. There's 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97, right? So we have what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So you have like a 1 in 4 chance of picking a prime number if you pick just a random number between 1 and 100. And what I'm saying is that you have about a 1 in 97 chance of picking a prime number if you just pick a random number between 1 and 10 to the 42. And so there are a lot of prime numbers. And so you have a reasonable chance of just guessing one of them if you guess enough times. And this is one of the keys of what we're going to be working on today. So you have a pretty good chance of guessing that a number is prime. But the issue is, of course, you don't know which number, you don't know when a number is prime. And checking that the number is prime takes a really long time. And so somehow we're stuck, right? So you know that if you guess 100 numbers, probably you're going to guess a prime number, but you don't know that that's the case, and you might fail at getting a prime number. Which brings us to probabilistic primality tests. So maybe even if you don't know that the number is prime, maybe you can guess, maybe you can figure out that it's probably prime, and this is good enough. And this is in fact what computers do. It's really hard for computers to figure out if the number is actually prime, but they can guess a number and then say it's probably prime. And this brings us to the Fermat Primality test, which is basically, remember, we have Fermat's little theorem, right? If n is a prime number, and a is any number between 1 and n minus 1, then a to the n minus 1 is congruent to n to 1 mod n, right? So this is one of the tools we've been using. And as an example, if n is equal to 11, then 2 is congruent to 1 mod 11. And 3 is congruent to 1 mod 11. Oh, sorry, 2 to the 10. And 3 to the 10 is congruent to 1 mod 11, and so on, right? So that was the point of Fermat's little theorem. If n is prime, then you know this to be true. But conversely, you can look at the other way. If a is any number between 1 and n minus 1, and a to the n minus 1 is not congruent to 1, then n is not prime, right? Because if it were prime, then they'd all be congruent to a 1. But if it's not prime, then, but if something isn't congruent to 1, then it's not prime. So as an example, let's say n is equal to 10. I want to prove that 10 is not prime. There are a number of ways you could do it. You could just factor it. But if it were a really big number, it might be really hard to factor it. And so instead, if I tell you that I'm going to choose the number 2, so I'm going to choose a is equal to 2. Well, then what happens? Well, what is 2 to the 9? Well, 2 to the 9 is congruent to 2 to the 8 times 2. Well, what is that? Well, 2 is congruent to 2. 2 squared is congruent to 4. 2 to the 4th is congruent to 16, which is congruent to 6. And 2 to the 8th would then be congruent to 36, which is congruent to 6. And so then 2 to the 9 is congruent to 2 to the 8 times 2, which is congruent to 6 times 2, which is congruent to 2 mod 10. And that, of course, implies that 10 is not prime. Okay? So this probably seems like a weird way of showing that 10 is not prime. Because, well, 10 is obviously not prime, right? But if instead of 10, I had a really big number, it would be really hard to figure out if 10 is prime or not. But if I could give you an example of some number a between 1 and n minus 1, such that a to the n minus 1 is not congruent to 1, then you would know that n is composite. I'm getting some blank stares, but not very many questions. So I will keep on going, but please do stop me when things when you formulated the question. Okay, and so this is basically a Fermat Primality test. Well, this is the Fermat Primality test. Basically, if I can give you some number of a, such that a to the n minus 1 is not congruent to 1, then I know that n is not prime. So this is a test, and it will tell me if a number is not prime. It won't tell me that a number is prime, but it will tell me when a number is not prime. And there are a couple other terms that I'm going to give. I'm going to talk about liars and witnesses. So the number a is special, right? Because if n is not prime, then I can have a number a that says that n is guilty of not being prime. And so we call it a witness because it tells us that n is not prime. Okay, so what does that mean? That means a number that such that, so we showed this on the previous slide, 2 to the 9 is congruent to 2 mod 10. So 2 is a witness that 10 is not prime. So imagine that you're in a court of law and someone comes in and you're on trial, and your crime you're on trial for is being guilty of being composite. And the question is, are you guilty? Well, if a comes in, a is some number, and they say you're guilty of being composite, then that a is a witness to the fact that you're guilty of being composite. Okay, so if I am able to give you a witness, then you immediately know that's not prime. On the other hand, even if you're not prime, you might have a number that says, oh, no, I think you might be prime. And then this would be a liar because it looks like n is prime, but it isn't. So for example, the worst kind of jury duty. Yes, can you imagine like being called up to jury duty and the entire point of it is like someone just gives you lots of equations and asks you to say, is this number prime? But yeah, so for example, 8 to the 8 is congruent to 1 mod 9. We can show this, right? Because 8 to the 1 is congruent to 8. 8 squared is congruent to 64, which is congruent to 1. 8 to the 4 is congruent to 1. And the 8 to the 8 is congruent to 1. And so then 8 is a liar, claiming 9 might be prime when it isn't. Right? And so somehow we have these ways of, so you have this test, but it doesn't always work because for some composite numbers, you will still get a to the n minus 1 is congruent to 1. And so if a number is actually not prime, if it's composite, but you have a number a such that it says, oh yeah, it looks sort of like it might be prime, then that's a liar. And so you have these witnesses and liars. So a witness basically tells you that n is not prime. A liar says, well, maybe n is prime even when it isn't. So how do we make use of this fact? Well, what we can do is, it's sometimes hard to find a witness, but if I gave you a witness, so for example, I'm going to claim that 129 is not prime. And as a witness, I call to the stand A is equal to 2. So what happens then? Well, then I wanted to compute 2 to the 128 mod 129. Well, I mean, you're going to have to compute this out. And because you don't know if it's prime or not, you can't use things like Fermat's little theorem or Euler's theorem or anything like that. You have to just compute it in the binary expansion. But we know how to do that, and it's not too terrible. But 2 to the 1 is congruent to 2. 2 squared is congruent to 4. 2 to the 4 is congruent to 16. 2 to the 8 is congruent to 256, which is congruent to 127, which is congruent to minus 2. 2 to the 16 is congruent to 4. 2 to the 32 is congruent to 16. And 2 to the 64 is again congruent to 256, which is congruent to minus 2. And 2 to the 128 is congruent to 4. So this is congruent to 4 mod 129. And therefore, we can say that 129 is not prime. Because we called the witness to the stand, and the witness showed that 129 is not prime. Does that make sense to everyone? So if I can give you this example, it's sort of like saying, if I know a divisor. So if I guess a divisor, let's say I guess this is divisible by 3. And then that would immediately tell you that it's not prime, because then you can divide by 3. And this is another way of doing it. You can just use a number and take it up to the 128th power. And then if it's not congruent to 1, then you know that it's not prime. Okay, try it out. Which of the following numbers is a witness to the fact that 33 is not a prime number? So hopefully you all know that 33 is not a prime number. It's divisible by 3 and 11. But, oh, is A equal to 2 always? No, it's not. So here, I'm having you check if A, which one of these different values. So these are possible values for A. Possible A's. In fact, you can choose any number between 1 and 32, between 2 and 32 as possible witnesses. So when you're a prosecutor, you're going to be calling different A's to the stand, and you're going to be like, oh, is this number prime? And they're all going to say either yes or no. And it's your job to figure out what a good witness is. If the answer is not congruent to 1, then it is not prime. Yes. 31 was right there. Had to have seen something, or he's an accomplice. But yeah, so the question is, which one of these is a good witness? And each one of these is going to say something, right? So like, for example, if I call a witness 1 to the stand, 1 is a terrible witness. You should never call a witness 1 to the stand, because 1 is always going to tell you, oh yeah, he looks like he's prime, because a 1 to any power is going to be equal to 1, right? And so 1 is the worst possible witness. You would never want to call 1 to the stand. And if you ever called 1 to the stand, 1 always just says, oh yeah, well, maybe he's prime. But some of these other numbers, sometimes they'll say that you're prime, and sometimes they'll say that you aren't. So would 1 be a liar? Yes. So if 33 is not prime, then 1 is a liar. Obviously, 1 is only a liar if the number is not actually prime. So 1 is always going to say that a number is probably prime. And if the number is actually prime, then it's not a liar. But if it is prime, if it's prime, then it isn't a liar. But if it is prime, if the number that you're trying to prove is prime is actually prime, then clearly 1 is not a liar. But if it's not actually prime, then 1 is a liar. So let's see. So 1 to the 32 mod 33 is congruent to 1. So therefore, this is not a witness, or it's not a good witness at least. And it turns out that this will be a liar, because we don't know this yet, because we don't know that 33 is not actually prime, but this will turn out to be a liar. Well, let's see. A lot of you have guessed 10. So what is 10 to the 32 mod 33? Well, let's figure this out. So 10 squared is congruent to 100, is congruent to 1. 10 to the 4th is congruent to 1. 10 to the 8th is 10 to the 8th is congruent to 1. 10 to the 16 is congruent to 1. And 10 to the 32 is congruent to 1. So this is congruent to 1. So this is also not a witness. Because 10 is going to say, oh, yeah, well, you look like you might be prime. So let's try a different one. What about 23? 23 to the 32 mod 33. Well, what's that equal to? Well, 23 squared is 529, which is congruent to 1. 23 to the 4th is also 1. 23 to the 8th is also 1. 23 to the 16 is also 1. And 23 to the 32 is also 1. So this is congruent to 1. And so again, this is not a witness. And let's try one more. So presumably this one's going to work. So I'm going to put in a different color. 31 to the 32 mod 33. Well, 31 is congruent to minus 2, which makes life a little bit easier. 31 squared is congruent to 4. 31 to the 4th is congruent to 16. 31 to the 8 is congruent to 256, which is congruent to 25, which is congruent to minus 8. 31 to the 16 is congruent to 64, which is congruent to minus 2. And 31 to the 32 is congruent to 4. So this here is a witness because it's telling you that it's not prime. And then that makes this a liar and this a liar. And this is also a liar. Okay, so whoever said that 31 must have seen something was correct. 31 is a witness to the fact that 33 is not a prime number. Does that make sense to everyone? So basically, I picked these particular 4 numbers, but and you can pick any number between 1 and 32 up to the stand. And you can be like, do you think that 33 is prime? Now, unfortunately, some of the numbers are going to say, oh yeah, I think he's prime, even when he isn't. Will it be multiple choice on tests, or will we have to find our own witnesses? You will have to find your own witnesses. So I've already posted the but for witnesses, you can choose any number between 1 and 32. And it turns out that a large number of numbers are good witnesses. So I made this multiple choice because I had to choose numbers that were liars. It turns out that liars are actually pretty rare. So most witnesses are honest. And so if you just choose a couple witnesses, you'll probably get one that's honest. In fact, I think these are the only only liars in the set from 1 to 32. And I had to pick them carefully. I think I need to double check again. But yeah, so let's sum this up. So in the Fermat Primality test, we want to know if a number n is prime. So maybe n is equal to 33. Well, the first thing you do is you pick a random number between 1 and n minus 1. Now, you generally don't want to use 1. 1 is a bad number. So really, you want to do, say, 2 to n minus 2. Because for complicated reasons, 1 and n minus 1 are just bad numbers to choose because they'll very often be liars. But a random number between 2 and n minus 2 is usually pretty good. So you might pick, say, a is equal to 10. Then you compute a to the n minus 1 mod n. So 10 to the 32 is congruent to 1 mod 33. If a to the n minus 1 is not congruent to 1, then n is not prime and a is a witness to the fact. Otherwise, n passes the test. And you don't know for certain. So here, you don't know. Because if you think about it, your number 33 is on trial. And a bunch of numbers, you have a bunch of witnesses that are coming up. And then n passes a bunch of people you've called up to the stand. And n passes if the number says, oh yeah, well, you might be prime. But on the other hand, if you repeat this enough times and it passes each time for sure, then maybe it's prime, but you can't prove it for sure. But if you do this multiple times, then you might end up with a different number, like a is equal to 31. And notice that 31 to the 32 is congruent to 4 mod 33. And then you know that 33 is not prime. No, so it's not a typo. Like you can choose any number between 1 and n minus 1, but it turns out that there are some numbers that are just bad witnesses. So 1 and n minus 1 are just bad witnesses. They'll often lie. You still can try them, and sometimes they'll work. Well, 1 will never work, but n minus 1 will sometimes work, but usually people ignore those 2 because they just turn out to be really like not very good witnesses. So yeah, so it's better to do 2 to n minus 2. Because 1 doesn't give you any information. 1 will always say, oh yeah, I think that number's prime. So on the practice quiz, which I posted as well as with solutions, I'm asking if a particular number is prime. I forget which number it is. But one thing you can do is you can just be like, oh yeah, well, I'm going to check a couple witnesses, say 2, 3, and 4 or whatever, and then check to see if they think that this number is prime. And you pick enough numbers. So realistically speaking, you should be picking random numbers because it turns out that this probability works out better that way. But if you just pick enough witnesses, you'll figure out if the number is prime enough, not with high probability. So let's go back. We have this big ugly number, right? I'm going to claim that 2 is a witness. And yes, computing list 2 to list power in mod this. So notice that if this is n, this here is n minus 1, and this here is n. So notice that one of them ends in the 6 and the other ends in the 7. So be clear that these are 2 different numbers. So 2 to the n minus 1 in mod n arithmetic. We can compute that. It's painful. I will never ask you to do this by hand. Are large numbers like this on the exam? No, numbers this big will not be on the exam. But a computer can do this. And using a computer, it turns out this is the answer for 2 to the n minus 1 mod n. And this is super ugly. And it takes a long time, even for a computer, this takes a little bit of time to take, but it doesn't take that long. So a computer can do this in a couple seconds. And this is not equal to 1. And therefore, the original number was not prime. I don't know the factoring of this number. All I know is that it's not prime because I have a witness for the Fermat Primality test. Or it'll, no, I don't think it'll take you 3 trillion years. I think you could probably do this in, let's see, how long would this take? This is 42 digits. So about 42 log, so about 150, let's say. So this would probably take you, I think this would take you less than a week. So I strongly believe that if you operated this carefully, you could do this in less than a week with a calculator, or with just a hand calculator. You might be slightly faster, but I think that any of you could do this in a week, assuming you didn't make any mistakes, which is quite possible if you're writing down numbers this big. But importantly, the point is that this is doable in a reasonable amount of time for a computer. And yes, this number is really big. And I chose it because it's a number that's too big for a computer to do it the ordinary way. But a computer can do this other way. And no, this will not be the final question on your exam. So you also have to remember that we have to grade your exams. And I don't want to read like 10 pages worth of computations and try to figure out where a number went wrong. But these techniques are really important because even though they're mostly useful for these big numbers, because for small numbers, you can often factor them. But for these big numbers, you really can't. But still, the sort of techniques that we've learned, and here we're connecting together what we've learned about modular arithmetic, which seemed like this entirely different number system, right? So we invented this new number system with modular arithmetic. And now what we're saying is we can use that new number system to tell us about primes in our old number system. And that's sort of the key here, is that we have, because we've invented this new number system, we have a quick way of figuring out if a number is probably prime or not prime. You, of course, have to be a little bit careful. So strictly speaking, Fermat's test only tells you when a number is not prime. Oh, so going forward, you should do n minus 2. It's more accurate. You can do n minus 1, but it just won't be as helpful. It won't tell you as much. If you do n minus 1, I'm not going to dock off points, but it will not be as helpful. And if I'm asking you to find a witness, choosing n minus 1 is not a good choice. Just like choosing 1 is not a good choice. But so strictly speaking, Fermat's test only tells you when a number is not prime. But it turns out that if you call enough witnesses to the stand, if you call enough people to the stand and they all say this number is probably prime, then maybe you have some confidence that the number is probably prime. And it turns out you can quantify this. So there's a weakness in Fermat's primality test, which is that there are a very special class of exceptions. These are called Carmichael numbers, which are not prime, but they look very similar to primes. Like Carmichael numbers have, they're like the mob bosses. So like they have an entire cohort of people they can call to the stand who are going to say, oh yeah, he's probably prime when he really isn't. But these Carmichael numbers are pretty rare. So we're going to ignore them for now, except for these Carmichael numbers. Each time a number passes the test with a different number A, you decrease the chance of it being composite by 50% each time. So each time it passes the test, it's sort of like doing a coin flip and being like, oh yeah, well, like if you pass the test once, you're like, oh yeah, well, there's probably a 50% chance that you are actually prime. You pass it twice, and you can be like, oh yeah, there's a 75% chance that you're probably actually prime. Pass it 3 times, it's more like 87% chance, and so on. It is a gift. Okay, well, I'll look it up after a JPEG file. So using n-1 for the power. Yes. So you have to use n-1 for the power because that's Fermat's little theorem. But then when we're picking a number to test, it's often best to pick between 2 and n-2. So, but I'll give an example here. So let's say that n is equal to 563. And this is not a Carmichael number. I will not give you any Carmichael numbers. You don't need to know, you don't really need to know this. I'm just saying this for completeness because there are a special class of really hard numbers. So it's not a Carmichael number. And what you have to do is you might be like, oh, well, what is the how, like if I want to prove that's composite, that's easy, right? In order to prove that something's composite, I just need to find a single witness that it's not prime. But if I want to show that something's prime, that's a lot harder because it's a lot harder to prove that something is prime than that it isn't prime. But if you pick enough numbers and you get that, so for example, if I did 231 to the 562 power mod 563, if you compute this out, it'll turn out that the answer is 1. So you can do this on the computer. If you do 108 to the 562 mod 563, the answer will also turn out to be 1. 7 to the 562 mod 563 will turn out to be 1. 499 to the 562 mod 563 is congruent to 1. Okay, and it turns out that you can keep on picking numbers, and the more numbers you pick where the answer is 1, each time it passes the test, you are more and more confident that you're actually a prime number. So the probability, because we've done the test 4 times, the probability of 563 is composite is less than or equal to 1 over 16, which then implies that the probability 563 is prime is greater than or equal to 15 over 16, which is greater than or equal to 93%. So we're able to quickly figure out if a number is probably prime or if a number is composite. And that's the whole point of these primality tests. And this is what computers actually do. So in your computer, when you're on some secure website, when you're on the chat website, which is a secure website, what you are doing, right, your computer's doing is it's picking these really large prime numbers and it's using those that are probably prime, and it's using those to communicate with my server. And we'll go over that a little bit more. So for the sake of completeness, I'm going to mention a couple other tests. So except for a certain class of hard numbers, these Carmichael numbers, Fermat's test tells us that a number is probably prime. There are other modifications that guarantee it. So there's a fancier test called the Miller-Rabin test. It's in your textbook, so you can read it if you want, and it always works. There are no hard numbers for it, so it works even for these weird hard Carmichael numbers, but it always works to show the number is probably prime. You can't ever prove that a number is prime without doing a full factoring, but you can show that a number is composite, and you can show that the number is probably prime. And so the punchline is this lets us guess a bunch of large numbers and quickly filter out the non-primes, because you can quickly find witnesses to show that numbers are not prime. And this lets you choose a large random number, large prime number. And these large prime numbers are essential in cryptography. And I think that basically ends my lecture for today. Just a reminder, on Wednesday, we are going to have a in-class interactive where we're going to talk about codes. I'm going to have you all write down messages and then try to break each other's messages. So a little bit of cryptography and encryption. And the next Monday, we'll be talking about how we can make use of these prime numbers to develop a new type of encryption that is, well, exactly what we're using for online security. And with that, have a marvelous Monday, and I will see you on Wednesday. Bye, everyone.